So hello and welcome to Machine Learning First Steps. Today we will introduce CNNs, which happens to be an architecture which is pretty useful for image processing and other multidimensional data inputs. So what are we going to do in this tutorial? We are going to understand the basic building blocks of a CNN and how a CNN works. We're also going to understand the strengths of a CNN, which qualifies us to understand also when do we need to use a CNN. So let's go. Today I'm going to give a very brief introduction about the theoretical basis of CNNs or convolutional neural networks. So basically, CNNs rose due to the need for an efficient and fast neural network learning scheme or neural network structure. So the basic problem with classic neural network architecture is that every unit happens to be connected to every other unit, which means we have a very large number of weights. So for each connection, we have a weight assigned. And for example, here we've got like so many weights. So this means the trainable parameters are many, and it is hard to train a network with such an architecture. If you want to delve deeper into more complex or a larger number of hidden layers, then that makes the training process very costly in terms of computation. So, for example, if we happen to work on an image, and images are known to have so many elements, so the resolutions of some images, now we have high quality images in our data sets. So basically that means we have a very large number of pixels, and each of these pixels will eventually be connected to some neurons. And in a deep neural network scheme for classification, we saw before that using a shallow network will not provide the best results. So in order to overcome that, one idea is, for example, to have an image like this. Maybe the order is not right because we got R, then G, and B, but it doesn't matter. We have three matrices, so let us just say we have like n times 3, for example. So instead of just flattening the elements of these arrays, we'll just take them as is, and instead try to apply a kernel or try to apply a concept called convolution. So basically, we have a filter or a kernel, which happens to be a matrix of an odd size. So for example, 3 by 3 or 5 by 5 or 7 by 7, something like that. And this concept is pretty famous in image processing applications, where they use kernels, for example, for edge detection or for gradient calculation and stuff like that. So the concept was adopted for machine learning instead. So basically what we'll do right now is that we will superimpose this kernel over the original image, and we start moving it or translating it along the dimensions of the image. So what we're going to do basically, when the kernel is placed over the original matrix, which happens to be of a larger size, for example, like that. So basically, we have some superposition between the elements of the matrix and the elements of the kernel, like this, for example. So what happens is that we multiply each element of the kernel times its corresponding element in the matrix. So we're going to multiply both layers together, and then we're going to add up the results of all of these multiplications and just get an output that looks like this. Maybe an output that is a bit smaller. The numbers, of course, I mean, don't mind the numbers or don't mind the dimensions here. But what I'm trying to say is that we're going to multiply all of these elements together and then add them up, then place the result in the very first element here in the output. Then we're going to move this kernel again. So what I'm going to do here is that I'm going to delete this kernel from this position and then make it move with a stride of 1. So a stride means the jump that you're going to take. So I'm going to move it like 1 unit to the left here, maybe. And then now we have a new superposition, and we're going to multiply the elements of that kernel by the elements or the corresponding elements of the matrix again, and then we're going to have a new output that we're going to place here. So basically, this process is known as convolution, which is a concept that is applied in both mathematics and physics, for example, for signal processing. So what this process does is actually the same thing that a neural network does, where we have some elements and we multiply these elements by a set of weights and then produce an output to a new layer. But the thing is here, the most important part is that not all the elements have to be connected to all of these weights simultaneously. So we have this kernel placed over a certain part of the image rather than just multiply all parts of the image by all the elements of this kernel or by all of these weights. So we have a significant decrease in the number of weights that we need to optimize in order to get a proper classification output. So this is one thing. The second advantage is that while I'm using the same filter or the same kernel for all parts of the image, one at a time, this kernel or this filter begins to learn features that may be useful for all parts of the image. So basically, we're learning how to share our parameters instead of having different parts of the image, with each with its own parameters. We are learning to share our parameters. So we're learning to optimize the same. It's like a socialist neural network where we learn to share our parameters, and that makes us more efficient because in an image or in any 2D or like maybe 2D or data having more dimensions than just 2 dimensions, usually it is the parameters that you learn for one corner of the image or one corner of that matrix or one corner of that data will often be useful for other parts of the image or the matrix or the data. So this parameter sharing technique happens to be more efficient, and at the same time it yields very good results. So this is the basic idea behind convolutional neural networks. So what we did here was the kernel part, which we call convolution, all right? So in this case, for example, since we're having 3 matrices, not just one matrix, so this filter will have also 3 versions. So instead of just having one kernel, this kernel will be, we can say it will copy itself into 3 different filters. Each of them will be placed on its corresponding color, for example. So, for example, for this first position, the 3 filters will be placed at the same exact time on the 3 components of the image, and we'll do convolution on each part individually. Then instead of adding just the output or the different multiplication outputs of one kernel, together, we'll just add the 3 components together. So instead of adding 9 components, 3 by 3, we'll add 9 times 3, which will be, I think 21. No, 20. I'm bad at math. So that will basically be 27. All right. So we'll have like 27 trainable parameters for this one convolutional operation, and then we will begin to shift our kernel to the right and pick up our stride. Maybe we need a stride of 1, so we'll move it 1 unit at a time, or maybe move it like more or faster, like 2 units at a time, for example. So basically we have some hyperparameters like the size of the filter that we're going to pick and the stride. Also, sometimes we add a parameter called padding, which means that instead of just starting here at the corner of the image, because we're missing out some elements, and the output will tend to be smaller, or the output image, or let's just call it the output, because the output is not necessarily like an image. It will look like something like that, for example, or sorry, it will be just one matrix, because we sum 3 matrices and we get basically one output, which is going to be eventually smaller, because this convolution operation just like is repeated for this section, since these edges are often ignored. So sometimes we introduce padding, like add a pad to this original image component composed of zeros, just to make the size a little bit bigger. So it's gonna be n plus, for example, you're adding 1 on the right and 1 on the left, so n plus 2 and n plus 2 times 3 instead of n times n by 3, in order to like get the same exact size as the input, instead of just having a smaller output. So this is a parameter that you need to determine as well, and you can use padding or not use it. It depends on what you want to do, or it depends on your design. The last parameter is the number of filters. You can actually apply many filters on the same input. So instead of just having one filter, which is basically this part here, we can have another filter and another filter. We can have like a finite number of filters. Like, for example, some people use 2, 3, 10, 30. You can use whatever you like. Right? So this is the convolutional part of the convolutional neural network. So another concept, or another layer type in convolutional neural networks, is called a pooling layer. So despite the fact that convolution operations have the same name as share the same name with convolutional neural networks, it gives you the feeling that they're just the only operations available in a CNN. But the thing is, we have another type of operations called pooling, which is pretty similar to convolution, except that pooling is usually used for getting either the maximum value or the average value of a certain part of the input matrix. So let's just say we have an input matrix like that, maybe a little bit bigger. Yeah, something like that. Doesn't look pretty good, but it will do. And assuming we have a new filter, but we call it like a pooling operation instead of a convolutional operation. And let's have another color instead of this color. Let's have just the blue color, for example, to indicate pooling. So what will happen here is that we will place this little pooling kernel here, and this pooling kernel will try to find like the maximum value out of all these 9 values and just put it in the output. So here we have like 4 times 4 input. So the output is going to look like, maybe we have 1, 2, 3, and then if we were walking with a stride of 1, then the output should be something like this. So basically, the equation that we use to determine the size of the output relative to the size of the input is gonna look like this. We get the number or the size of the input, and we add the padding to that. So since you have part of the padding on the right and another part on the left, and they're both like identical twins, so you multiply that by 2, and you subtract the filter size from that, and then you divide it by the stride, and then you add 1. So basically for this particular, and this equation works for both convolution and pooling. So basically here we didn't use pooling, and we have a stride of 1. So basically we have n, which is 4, minus f, which is basically 3, plus 1. So this should produce a 2 actually. And 4 minus 3, which is 1 over 1 plus 1. Yeah, it should be 2 by 2, something like that. Well, doesn't quite seem. Yeah, actually it's going to look like 2 by 2. Actually, it makes sense. All right. So this is basically the output, and the output of the pooling. For a max pooling operation, we pick the maximum value inside of that partition of the matrix. And for average pooling, we pick the average value of all of these, or all of the elements of this partition. We use max pooling more often than average pooling. Average pooling is actually rarely used, but sometimes it's used. It depends on the design as well, but max pooling is much more famous. So this is basically the pooling operation. So right after that, after we're done with the convolutional part and the pooling, we usually flatten the elements that we have or the outcome that we have. So instead of continuing a series or an endless series of convolutions and poolings, we just, at some point, we get a matrix that might look like that. So it has a small dimension, but thing is, it will most likely have like a huge channel size. So for example, when you start with an image, you start with an input, which is basically n times 3. And this n happens to be large, while the number of channels of the input happen to be small, like 3, for example. But then, due to the many filters that you use, usually like the size of the image itself shrinks. But because you're using so many filters, that means you have so many output channels. So basically, you'll end up with something like this. And when you feel like you or your input image shrank in terms of size and has a large number of channels now, you can flatten that, and you can pick just the elements and you do the normal flattening thing. And then you start dealing with a normal neural network. So basically, the end of a convolutional neural network is actually a very normal neural network. And we tend to call that output neural network a fully connected layer. And we call it that because now we have all of the input elements connected to all of the elements of the next layer, which means that there are so many interconnections. So this is fully connected, not just having weights assigned to certain partitions of the inputs. So basically, a CNN would look like this. So usually we start, for example, with an image or any sort of 2D data, or maybe more even, so it looks like a matrix of sorts. And then we start to shrink the size by applying, for example, convolution, and the number of channels increases, so you reduce the height and width while increasing the depth. And then we apply, for example, usually we apply like 1 or 2 convolutions, so maybe 1 or 2, maybe more, depends on the designer as well, but usually 1 or 2 maximum. And then we apply pooling, for example, like to reduce the width and height again, while keeping the number of channels either constant, like the same as the convolutional layer, or maybe basically, yeah. Then we apply maybe another convolution pooling layer. So usually we call this a convolutional layer. Instead of, well, the basic concept is that is the convolutional layer. The thing is, some designers refer to this entire unit or this entire building block of the network as a convolutional layer. So, it's open for interpretation. Some people just call the convolutional layer here a convolutional layer. Some people include the pooling layer as part of the convolutional layer. So it doesn't really make a difference as long as you understand the basic concepts here. And then you might apply another convolution, for example, in order to further reduce the width and height while increasing the number of channels. And then another pooling maybe. And then at some point, when you feel like you're done with all of these convolutions, you will shift to a flattened version of the activations or the outcomes of the last layer. And by the way, while performing your convolutions, you might apply, for example, an activation here, like a ReLU, for example. Actually, this is the convention that is most likely followed in most designs, because a kernel in itself is a linear operation, and we don't use linear operations for complex learning. So we might multiply that, or we might use these convolutional outputs and apply a ReLU activation function on each of the units individually, same way we do in a normal neural network, in order to get some nonlinear activations that would help the network learn better. And then after we're done with that, and after we get the fully connected version of that, or we get the flattened perspective of the activations, we usually apply some, or we usually include some fully connected layers, which is basically like a normal neural network, a very normal neural network, and then end with a softmax layer here for decision making, or for producing individual probabilities for different classes. And that's it. This is basically how a CNN works. This is a very brief explanation, and I may have omitted some details because they are out of the scope of this little course here. What we're more focused on is on how to apply new CNNs in order to solve actual problems. So in our next session, we're going to work on a classification problem which has to do with CNNs, and we're going to display how accurate a CNN can actually get and how it manages to learn fewer parameters while achieving better accuracies than normal deep neural network. To summarize what we did today, we now understand how different neural network architectures work. We were introduced to linear regression, logistic regression, neural networks or shallow neural networks, and deep neural networks, and now we saw another deep neural network scheme known as CNNs. There are still many architectures listed in the literature, but you're now ready to understand how different architectures work based on your basic knowledge right now. So if you're going to pursue a career in machine learning, you're now ready to be an active learner, or an active machine learning learner. So now we are ready to use our software tools to develop a CNN for another multi-class classification problem, which happens to be more complex than the other problems we used to deal with, and we're going to see with our own eyes how CNNs perform much better than other schemes.